Now, what happens if we're doing an interval estimation where we do not know what sigma is? So the confidence interval on the right has that issue, and we don't actually know what that sigma is. So sigma is the population standard deviation, but it is really rare for us to understand what that value is. A good estimate, therefore, for sigma is the sample standard deviation, which is known as S. But this actually creates a new problem. By using the sample standard deviation, additional error has been introduced. And thus, there are two parameters that are being estimated from the sample, x bar and S. This makes the value of z a bit too narrow since it assumes a standard normal distribution. But there is a distribution similar to z, but provides more room to account for the error, and it's known as the student's t-distribution. The student's t-distribution, or what we like to call as the t-distribution, looks very much like a normal distribution, with a classical bell shape. But the tails are slightly higher, and at the center, it's a bit lower than the standard normal distribution. Using the t-statistic instead of the z-statistic will widen the confidence interval of the sample with the same confidence level. As you can see here in the chart, it looks very much like a normal distribution, and the curves to the left are different t-distributions. The topmost line in black is the standard normal. It's very hard to see, but it is the topmost line. And then the red and blue are different t-distributions with lower degrees of freedom, which we'll show in a second. If you look here at the top, it demonstrates how close it really is. That blue line is the one that's furthest away. And it's furthest away because the degrees of freedom is lower. It's 6. The red line's degrees of freedom is 9. And this is what is causing this difference. Okay? It is the only parameter in a t-distribution. It's called the degrees of freedom. The higher the degrees of freedom, the closer it will be to the standard normal curve. The number of degrees of freedom is directly related to the amount of data in a sample. Specifically, it's just n-1. If you have 100 data points, your degrees of freedom will be 99. If you have 50 data points, your degrees of freedom will be 49. Okay, take a sample with 5 data points where 4 is known. 5, 10, 8, and 7. We don't know what that fifth one is, so we'll call it Q. The sample average of the 5 data points is 7. Therefore, the final data point could be computed clearly as being 5, because if we add the 5, 10, 8, and 7, we have 30. We know that the average of the 5 data points is 7, meaning that the sum had to be 35, and so therefore the final point has to be 5, meaning in the sample of 5, 4 data points can vary, and the last data point could easily be computed. Therefore, the degrees of freedom is n-1. So where n is equal to 10, the degrees of freedom is 9. Where n is 30, the degrees of freedom is 29. Where n is 1,000, the degrees of freedom is 999. Returning to the issue of the unknown sigma, the sample standard deviation S was used instead of the unknown population. So that area in red, we don't know. What we're going to do is we're going to change it to be a t-distribution. The z-statistic becomes the problem because the two statistics, x bar and S, are estimated from the sample. Using the t-distribution will provide us with a more conservative estimate to ensure that the confidence interval accounts for this. Thus, the formula becomes x bar plus or minus the t-distribution with a certain degrees of freedom. So assume we have a set of 50 grades with a mean of 88 and a standard deviation of 4.67. Provide a 95% confidence interval around the mean. N is equal to 50. The mean is 88. That's our x bar. The standard deviation is 4.67. That's S. The confidence level equals 0.95, and our alpha, therefore, would be 0.05. Since the data set in the sample and the population standard deviation is not known, the t-statistic needs to be used in the formula. Therefore, the formula for the confidence interval is given by t alpha over 2 degrees of freedom times S over the square root of n. Our next step will be to take that information and start plugging some things in. So we can compute our degrees of freedom, because that's 50 minus 1, which gives us 49, and alpha over 2 is 0.025. The third step is now to compute that t-statistic. In order to do that, we're actually going to use the Excel function t.inv. Now, t.inv of 1 minus that alpha now is going to give us t.inv of 0.975 with a degrees of freedom of 49. And therefore, the t statistic is 2.009. We can now compute the interval. So assuming that we have those test scores and are looking for that 95% confidence interval, we now can plug in the numbers. We know the t-score is 2.009. We will multiply that by 4.67 divided by 7.071. And this will give us an upper bound of 89.334 when we add that to the 88 as the average, and an 86.667 when we subtract it from 88. Therefore, the confidence interval can be written as 86.667, 89.334. Now, from the previous slide, we showed how to get the t-statistic using Excel. But there are a bunch of ways that we could actually get that using a couple different functions in Excel. Again, we're looking for this blue region here in this t-distribution. So assume alpha was 0.05 and the degrees of freedom is 49. Then alpha over 2 is 0.025. We can use the t.inv function, but we would have to use the alpha over 2 instead of alpha, but the same degrees of freedom of 49, and that gives us 2.009. Excel also provides a t.inv.2t, meaning a two-tail function, which would be using 0.05 as the alpha, which would automatically take care of the two tails for you. And that also yields 2.009. The other thing we could do is if we use the t.inv, but we use the 0.025, which would be representative of the left side of the curve, that would give us a negative value. So we could just use the absolute value to get the same 2.009. It is important to have sample sizes large enough in order to create a reasonable confidence interval. Previously, using the central limit theorem, when n is greater than or equal to 30, the dataset approaches normal. The key is that the dataset should be at least approximately normal. And with the dataset sufficiently large, this shouldn't be a problem. One way to check would be to use a histogram. Here we can see on the left, it's kind of normal. It's got a little bit of a higher tail on the right, but it's probably going to be close enough. And on the right side, it's not so normal. That definitely has a tail, and this does not look like a normal distribution. Even though both datasets are 30 observations, the data on the right could be problematic because it really doesn't resemble a normal distribution. In this case, the confidence interval really won't be as accurate. A confidence interval can still be produced, and you can use it, but it should be noted that since the data is not approximately normal, it won't be accurate, and you should denote it as such. Smaller data sets are also problematic. Consider a data set with 5 data points, 10 data points. Consider a data set with 5 data points, 10 data points, and 20 data points. If the data was produced from an approximately normal distribution, the smaller the sample, the less accurate the confidence interval will be. In the top left here, we have a normal distribution with 20 observations, and that kind of looks normal. In the top right, we also have n equals 20, but in this case, it doesn't really look that normal. In the bottom left, we have 10 observations. That definitely doesn't look normal. And the bottom right, we have 5 observations, and this clearly has a problem that almost looks more uniform. Therefore, when collecting data, it is useful to identify a necessary sample size needed to get a specific margin of error. Assume a small survey was conducted in which the information on the right was found. So we have a mean of 107, standard deviation of 5, and with a sample size of 100. The confidence interval for the data is going to be 107 plus or minus this t-distribution times 5 over the square root of 100. And the margin of error becomes 0.993. What if we want to cut that in half and make the margin of error 0.5 or less? First, let's isolate the margin of error from the formula. So we're going to take that plus or minus stuff to the right, and we're going to actually set it equal to 0.5. Now recall that the t-distribution that we had required a degree of freedom which was based on the sample size. However, we're trying to find the sample size. Therefore, we really can't use the t-distribution. But the t-distribution could be replaced by the z-distribution or the normal distribution. Again, we could do that because they're very similar. And it doesn't require a sample size. Further, we're going to take that denominator, which had the square root of 100 before, but since 100 was the sample size we had, and we need to figure out what sample size we really need, we're going to revert that back to the square root of n, since n is what is being sought. And then we're going to calculate that z-statistic, which we know is 1.96, again, using a 95% confidence interval. And now we have a formula, and all we need is a little algebra to solve for n. Solving for n, we end up with 0.5 equals 1.96 times 5 over the square root of n. We'll just bring that square root of n over to the left side, and we have 0.5 times the square root of n equals 1.96 times 5. We'll then divide both sides by 0.5, so now our formula becomes the square root of n equals 1.96 times 5 over 0.5. And to get rid of the square root on the left side, we're going to square it. Again, taking the square of a square root will give you the value underneath the square root itself. So that becomes n, and then we will basically square the right side. This now says that n is going to be equal to 19.6 to the power of 2. Again, we computed the stuff inside of the parenthesis of 1.96 times 5 divided by 0.5, which gave us 19.6. When we square that, we end up with 384.16, and therefore, because this is a sample size, 384.16 doesn't mean much, so we're going to just round that up to give us 385. Remember, if you do round, that's going to drop it down to 384. We want to make sure we go up to 385. And so therefore, the sample size to cut the margin of error in half is going to be 385 in this case.